algebraic groups as automorphism groups of something to view them as fibrations. And so I'll explain all of these notions, what I mean by them. The motivation for doing such a thing was to study exceptional groups and to study the formations of the algebras of which the exceptional groups are automorphism groups. So when I say exceptional groups, I mean in the sense of the Cartan-Killing classification. So as you know, there are the four infinite families of algebraic groups of type AN, BN, CN, DN. And I explain exceptional groups. So G2, D4, F4, E6, E7, and E8. And so reasonable people would maybe not say that D4 is exceptional, but I do because of its thinking diagram having this diagram automorphism of order 3. So that's why here's a curve. And the way this started is, I very much enjoyed Cheryl's talk this morning about collaboration. The way this started is that Philippe Gilles was studying groups of type G2 and D4 in terms of torsors and with very heavy algebraic geometry machinery that I knew nothing about. And I had worked with these groups viewed as deformations of octonian algebras. And so we came together and this resulted in the paper. So that's another way, or one of the ways you mentioned collaborate. All right, so let me get to the definition. So what do I mean by an algebraic group? So I take K to be a unital commutative ring. So unital commutative ring. And this can be any unital commutative ring. You can think about K as a field. That's why the letter K is chosen, but this should work in greater generality. Does work in greater generality. And so when I say group or algebraic group, so what I mean is a K group or an affine group scheme over K. So this is a representable functor G from the category of K rings to the category of groups. K rings, that's K algebras that are unital commutative. I avoid using the word algebra because to me an algebra is not necessarily commutative or associative or unital. So these are rings that are algebras over K. And to each such ring, you get the group G of R. If you don't like to think about it as functors, think about it in some other way. That will not matter for this talk, but just to fix the notation. And so perhaps an easy example is the group SL2 that sends a ring R to SL2 of R. So that's the set of 2 by 2 matrices, you know, in R such that the determinant is 1. But more often than that, I'll look into groups that are automorphism groups of algebras. So A here is an algebra that is not necessarily commutative or associative. But what I do require is that as a module, A is finitely generated projected. K mod. this is the appropriate generalization of the infinite dimensional to moving over rings in setting. And so what does this do? It sends a ring R to the group of R algebra automorphisms of a scalar extension by R. So that is one example. And another example is if you have a K module and F from M to K form, quadratic form, or cubic form, or some other degree form, then you can study the group of isometries with respect to that form. So that sends R to the set of all phi from M tensor R to R that preserve this form. So F after scalar extension to R is unperturbed by phi. And so what am I trying to get at here? By viewing algebraic groups in the extent you can as automorphism groups or as isometry groups of something, one can use explicit knowledge about this something to understand the group better. And the example, so the idea is to use A and F to understand G and H and some notion of the quotient. And I want to give you an example of this where from recent work where we apply this to a particular kind of groups. And for change, let's suppose that H is a simple group of type F4. So that is one of the exceptional types. Then H is the automorphism group of some algebra. Every such H is the automorphism group of what is known as an Albert algebra. So what is an Albert algebra? It's an exceptional Jordan algebra. This is turning into one of those Wikipedia rabbit holes where every definition you click on, you get a new word that you have to click on that. So what is a Jordan algebra? A Jordan algebra is an algebra that is commutative, not associative, but satisfying some weak associativity that left multiplication commutes with multiplication of the same element. So x squared xy is the same as x squared y. Where on earth would you come across such a thing? So if you think about Lie algebras, what is one way to get a Lie algebra? You take an associative algebra, forget about the multiplication, use the commutators. This gives you a Lie algebra. If instead you use the anti-commutator, you get a Jordan algebra. So Jordan algebras are anti-commutator algebras. Can you get every Jordan algebra as a subalgebra of an anti-commutator algebra, of an associative algebra? Yes, unless by definition it's exception. So the exceptional ones are those you cannot get as anti-commutator algebra. And those are the Albert algebras, or exceptional. I should say that the definition that I'm giving here requires two to be invertible. For for fields of characteristic 2 and that kind of things, you need more technicalities. And so over algebraically closed fields, and this, let me just to simplify, say K field. Okay, so over algebraically closed fields, there's a unique exceptional Jordan algebra. And every other exceptional Jordan, or general fields, every Jordan algebra becomes this unique exceptional one after scale extension. And so what is more interesting about these Albert algebras is that there is a cubic form F from A to K, and the isometry group of F, let me write it sloppily, is of type E6. Okay. So now I have a group of type E6, a group of type F4. And what this gives is a sort of, the automorphism group sits inside the isometry group. Let's call this G, and it contains, H as a subgroup. So you can form some sort of quotient, and you have G as a fibration of this over this quotient. And this, what is this quotient? This is an FPPF quotient. It's a horrendous thing. It uses this fatefully flat topology. It's constructed as the sheaf associated to some pre-sheaf. So this is horrible. That's somehow what we need to know about this. So we want to give this some meaning and some concrete understanding. And so this was what I was looking for a couple of years ago. And what I got is that this group G acts locally transitively on some scheme or variety that I will call S3, which is X3, which is simply the unit sphere of this cubic form. Let's say not so much of a sphere, but it's the unit thingy. And the stabilizer of one of the points in X3 is this group H. So the upshot of that is that now we have G mod H, this quotient, is represented by this variety or scheme. So this gives us a concrete understanding of this quotient. And now we have a fibration. So I can view the group G over this X3. And the fibers are H torsors. So let me stop a bit and talk about what this brings us. So I have the bigger group of type E6. I have this concrete variety, and I have a projection, and the fibers, well, the fibers are as large as the group H that I'm quotiented with, and they are H torsors. This means that the group H acts on them locally transitively. I'll come to what locally means. So over every point of this thing, I have pi inverse of x. So either pi inverse of x is empty, or H acts freely transitively on it. And after a reasonable extension, it will become non-empty. So non-empty after FPPF extension. So what this means is that this quotient projection is not surjective. This is the meaning of this FPPF quotient. But it becomes surjective after an FPPF ring extension. What is an FPPF ring extension? If K is a field, this just means a finite field extension. So over rings, this is what generalizes finite field extension. In particular, it doesn't require the extension to be separable, it's just some finite field extension. And since anyway, everything I'm working on is finite dimensional, finitely generated, the finiteness of the finite field extension is not important. And so FPPF stands for faithfully flight of finite presentation. And I'll let you figure out why flat is spelled with a P.
Can I ask a question? You say a cubic form.
Yes.
I think of that of a homogeneous polynomial.
Okay.
But that requires variables. Yeah.
Yeah.
So how many variables are you dealing?
That's a interesting question. Thank you. So this Albert algebra is 27 dimensional. So this is of dimension 27. And so if we do the math, this X3 is going to be 26 dimensional because it's a hypersurface in the Albert algebra. And G is the group of type E6, so it's 78 dimension. And the fibers have an F4 action. F4 has dimension 52. And you can check that 78 minus 52 is this. So that's how this works. Okay, so what is the gain of all of this? Why do we do this? Well, it depends on if you come from algebra or geometry. So what is the point of having a torsor? Torsors, in French, that just means twisters. So they're used to twist the multiplication of the algebra. And from an algebra side, this is satisfactory because you can show that there is an algebraic notion of an isotope, which are classical non-associative algebra twists of Albert algebras or any Jordan algebras. And this gives you all the isotopes. So you twist by these torsors as X traverses this hypersurface, and you get all the isotopes. So since this is more of an algebraic group workshop, I'll maybe say something about the interest in terms of groups. So this is interesting because you can view larger groups as fibrations over smaller groups. So here you get E6 as a fibration over this X3. And let me put F4 on the fibers to say that they are F4 torsors. They're basically twisted copies of them. And then you say, okay, but let's try to understand groups of type F4. Some of them you can view as fibrations over some other surface where the fibers are of type D4. And this was in this paper dimension. What about groups of type D4? You can view them as fibrations over some surface of type X1 with fibers, I call X1 with fibers of type G2. And this was in this collaboration with Philippe G from 2019 that I mentioned. And in the same way that Albert algebras figured here, Octonian algebras figured there. And I'm going to be doing this. So now you can use groups of type E6 to bring groups of type E7 as fibrations over something. And just last week, together with Yari Desmet, we managed to show that certain groups of type E8 can be viewed as E7 torsors over some space. And so this is somehow the program of using these things to view larger groups as fibrations over some concrete surface using these algebras. And so this uses so-called Brown algebras, and this uses the algebras of type E8. There's a particular construction called the Tix-Cantor-Cacha construction. And so the thing that I want to remark is that the xi are explicitly constructed from concrete algebras. They cannot just be generally, you have to look into the situation. This is why it takes time. But this is a feature and not a bug, because the whole point is that we want to have some concrete thing to understand this FPPF quotient. And so in the last couple of minutes, let me mention two types of open problems. So this was somehow a research direction that we have been working on for the last couple of years. And so the first open problem is, what about other groups? So I told you that every group of type F4 is the automorphism group of an Albert algebra. But not every group of type E6 is the isometry group in the way that I presented it here. But it's locally that. So how do we get those other groups? And also, I've been looking at exceptional groups, because somehow for other groups that are not exceptional, you can do things more systematically. But what does this say about other groups of also these types? So for example, in type AN, you have the automorphism groups of central simple algebras. What happens if you try to embed groups of type n-1 into that? And all of this requires somehow, the whole point of this is that you combine the point of view of algebra, like these algebras, Albert algebras, and so on, with these torsors. And this leads me to the second open problem, which is if you take a reductive group and you realize it as the automorphism group of something. So as Alistair and other people in the audience are experts on, you have all of the subgroups here. So from the reductive group side, the subgroups, you have tori, you have unipotent, you have parabolic, and so on. And if you view it as the automorphism group of something, then you have stabilizers of elements, of subspaces, of subalgebras, and also you have fixers or fixators. I don't know how to say it, but like a stabilizer of an algebra might move things around inside the subalgebra, but the fixator fixes this algebra pointwise. Okay, so what is the relation between? If I give you a group as a stabilizer, can you tell me how it behaves in terms of some composition into these groups, and vice versa? So this was needed by Mathilde Macquin in 24, because she studied quotients of groups of type G2 in small characteristic by maximal parabolic sum. And so she needed the octonions to describe this. Last year, a master student of mine, Sophie Potrel, who will be doing her PhD with Miko, looked into this closer for groups of type G2. So what we hope for is a dictionary to somehow get an even closer link between algebra and geometry. And very arrogantly, I'm going to stop here and leave in 2 days, and I will just assume that you'll be working on this for the. Thank you for your attention.
Any questions? Comment? I have a question. So when you first wrote that, I thought, I'm following because there is a cubic form in 4 variables, I guess, that has an E6 singularity and is unique. And I thought that's what you were referring to. And then you went and told me, no, it's 27 dimensional. And then I felt humbled, I guess. So there's no connection to this.
No, I'm sure there is. You can, specialize in some. So these Albert algebras, you can write them as 3 times 3 Hermitian matrices with respect to octonian algebras. And then you have the diagonal elements, and this could be something like that. I'm not sure, but I'm sure it's related.
So you're here for a while?
For
a few days.
Until Wednesday.
Yeah. Oh, until Wednesday. maybe at least I can point.
Yeah, sure.
There's no reference between this and the singularities that help me or not.
So I'm deliberately choosing f of x equals 1 to have a smooth variety. Choose f of x equals 0, or look at the corresponding projective variety. Somehow then you get some singularity. But the singularity, I think maybe you probably get one singularity, and that is probably the one you're looking at, but I don't have a mathematical statement.
All right. Thank you. Any more?
If you do it over somewhere that's probably like an algebraic closed field, which is probably not the reason to do this, do you get back some nicer description of your xi's? Because like when you draw that, I just think of the fact that the 26 is the complement to the Lie algebra and the algebra B6 for F4.
Right.
And so do you get back something that if I, in my, the world I tend to live in of algebraic closed fields,
right.
I get something.
So this just as you said, this is mainly, of course, it works over algebraic closed fields. But the point is, for all of these groups, there's a unique group of each type, so you don't get much of twists and so on. But if you take, I'm somehow interested in this because my PhD students working on this for groups of type G2, and this involves torsion over manifolds. But anyway, you have a Lie algebra here, G, and if you, this complement is probably the sort of the quotient in quotient space as a space, and then you look at that. I would guess that this would be precisely it. But also because this FPPF quotient will, its rational points over your algebraic closed field will be every. So this is actually going to be surjective, and then this probably will be what you're thinking of.
How is it following some kind of pattern with the algebras that you're seeing? Is in Kac-Moody groups, you can get Kac-Moody groups of type E9, E10, E11. Is this something that you could? Will there be
that's interesting. So I don't know what happens in those types. It's actually already in E8 it breaks down. So the point is that for E7 and below, these are automorphism groups of lower dimensional algebras. So this Brown algebra is 56 dimensional. But in E8, the Lie algebra of type E8 is of course also 248 dimensional as the group. So there it breaks down this thing that so it's rather not a system, but somehow the exception to the system that there are these let's say sporadic, in some sense, algebras that pop up that happen to have these automorphism groups. In my mind, this is the raison d'etre for these groups. But this breaks down in E8, and I don't know what happens. So do you have you need some model on which the group acts, and then you find some invariant subset inside this, and you show that this is a smooth scheme, and then you work. So that's somehow the idea. It's not a general system.
So was it just like the questions of did you have like you obviously eventually had to go to a Lie algebra of type E8
Yes.
to do that one, but presumably that wasn't your starting point of trying to do that?
Well, it kind of was. It started. So this is 248 dimensional. This is 133. So we need something 115 dimensional. And then we looked into the literature, and back in the 80s, Imai Yokota, two mathematicians in Japan, they looked into this for real Lie groups and constructed some variety. And we thought, okay, this variety is a starting point. We tried to look at it. So we didn't have any other algebra, but this dimension is almost 2 times 56. So for the longest time, we thought maybe we needed pairs of Brown algebras, and in some sense it is, but this is what the TKK construction does.
What is 2 times 56 is 112.
12.
Yes, which is E8 minus the dimension of E781. So there's a connected subtype A1 in.
Right. Yes, so this is probably the so this TKK construction is a 5 grading of the 8 algebra. The 0 component has dimension 134, so that's E7 plus.
Yeah,
that's a total. Yes, so that's exactly how the
So you really need E7.
yeah, exactly. And this is why, I mean, then you get it as a vibration. So it's somehow that. So, but then again, I mean, this question, I mean, I'm ignorant of these connections. And so how do you connect this group into this more precisely?
You should probably wrap it there, I think. Questions? Right. Thank our speaker again.